Today we will discuss another example of our automatic control system, automatic closed loop control in our process industry. So now this example includes the application of a process plant or process industry. You will study this type of process in your next subject, that is the process control. So now today our control is a level control loop. Level control. So in this case we have a tag. Inside that tank we have some water. So the purpose of this system is we have to control the level of water. Now this tank should have a inlet flow and there is a outlet flow. So this one is inlet flow and through this outlet there is an outlet flow. This type of process is used in our process plant to supply water to the various processes, and this flow depends upon the height of this water level. So if the height is increased, then we know due to the pressure at the bottom, the outlet flow will be increased. So that's why this type of level control loop normally used in various types of processes. So now our intention is to control the level of water inside this tank to a desired value. So our target is level control, level to be made constant to a desired value. Now suppose this desired level is now 500 meter from the bottom. So this height is 500 meter. So we have to maintain this height to 500 meter always by the use of some control. Now for this purpose we have to sense this level using a level sensor. So this level is sensed by a level sensor at first. Now the output of this sensor will be delivered to the transmitter. and the output of this transmitter will be supplied to the controller. So one input of the controller is coming from the transmitter. Now another input of the controller will be the set point value or reference value. Now the output of the controller will drive a control valve. This one is control. Now let's explain what is the function of this transmitter. That means from the output of the sensor is in the form of voltage, normal. Now this sensor is placed very near to the tank. That's why this sensor, this instrument is called field instrument. So this type of instrument or device will be placed near inside the field where the process is going on. So the tank is our process, the liquid level which is to be controlled. This is our process, and near this process we have to place the sensor. And the output of the sensor is in the form of voltage. Now this controller is normally placed far away from the field. It is the normal convention of a industry. So normally the controller is not placed very near to the field. It will be placed inside the control room, and that control room will be very much away from the field. So we have to transmit this output voltage of the level sensor to a long distance, passing through a long distance. So if we transmit this signal to a long distance in the form of a voltage, then there will be a huge problem. What is this? We know that is, if this voltage is transmitted in the form of voltage, then there will be a huge voltage drop due to the resistance of the conductor. This one is a copper conductor or cable, or it is called cable loss. So due to this cable loss, that's why there will be I into R, current into resistance. This will be the voltage drop across the cable. So due to this voltage drop, a huge voltage drop will be occurred, and due to this voltage drop we will get very much less voltage at the control. Okay, done. So now the question may arise, so what will be the problem? There is no problem. If the voltage drop is fixed, then there will be no problem. If this voltage is suppose 5 volt and the voltage drop is suppose 3.5 volt, then at the controller input we will get 1.5 volt. No problem. If we will get 1.5 volt constantly, then there will be no problem. Then we can understand, if the voltage is 1.5 volt, then it will be 5 volt. Again, if the voltage is 4 volt, suppose this voltage drop decreased to 1. So if this type of voltages are fixed, then there will be no problem. If controller will get 1 volt, it will understand at the output of the sensor it is now 4 volt. But this is not happening at all. Because due to the ambient temperature, as this lake is very much large, there is a long distance. So there will be various types of ambient complications. There may be some moisture, there may be some temperature difference. In night, there will be huge fall of the temperature. At day, there will be rise of temperature. So due to these factors, the resistance of the cable will not remain constant always. So as the resistance will not remain constant, that's why the voltage drop also is not a constant. So it will vary time to time depending upon the ambient condition. So that's why this voltage will not remain constant. This will vary also. So if this voltage is varying due to the voltage drop, but there is no change at this voltage. The output of the sensor is constant. It is 5 volt. But due to the change of this voltage drop, time to time basis, there will be a change at the input of the controller. So one time it will be 1.5 volt. Then after half an hour, it will be 1.4 volt. Then 1.8 volt. So there will be some constant fluctuations. So if this fluctuation is happening, then controller cannot understand what is the actual voltage at the side of the level sensor. It cannot predict. It is not possible for the controller to predict the output voltage of the level sensor correctly. So that's why there is a very much important function of the transmitter. So what is this? That means the function of this transmitter, it is basically a voltage to current converter. So what is the function of the transmitter? It is basically a V to I converter. So what is the property of this V to I converter? We know that is the V to I converter is basically a constant current source. That means this current will depend upon the input voltage. That means there will be a relationship. That means current I will be directly proportional to the V. This one is the input voltage, this one is the output current. And this current will remain fixed until there will be no change at the input voltage. So that's why this current is a constant current. So the transmitter will deliver a constant current at its output. So now we know if we will transmit the voltage into the current form. Now this signal is not transmitted into the voltage form, it is converted to the current, and that current will be transmitted through a long distance to the controller. So if this is happening, then we know the current does not depend on the resistance of the conductor. Okay, as it is a constant current source, that's why this current remains always constant. It does not depend on the resistance of the conductor, because we know this is the symbol of the constant current source. Suppose this one is the conductor resistance. Okay, this one is the I, this R. So if this R is varying, although there will be no change in the value of the I. So I remains constant. It does not depend on the value of this R. So the same thing is happening in this case. Also there is a change in the conductor resistance or the cable resistance, but there will be no change in the current. So that's why this current will be transmitted as it is towards the controller. Now controller will get this current, this input as a current form. Now the problem is solved. As this current is constant, although there is a fluctuation of ambient condition, but there will be no change in the current. So this one is the function of the transmitter. Then controller will convert this current again into the voltage form towards it. What is this? Then this current is basically passed through a resistance. Simple resistance. And the voltage drop across this resistance will be taken as the input to the controller. So this one is again a I to V conversion near the controller section. Okay. Now this voltage will be fed to the controller. So at the input, actually the controller is getting the signal in the form of voltage, but before it there will be a conversion from current to voltage, and this current to voltage conversion is also happening very near to the controller. This system is also placed inside the control room. It is not placed at the field. Okay, so this voltage and now this set point voltage will be compared, and accordingly the controller will take the decision, that is the control valve opening is to be increased or control valve opening is to be decreased. So what is this control valve? This control valve basically is called, this one is a final control element. This control valve is basically called final control element, or in short it is called FCE. So what is this control valve? Basically inside this control valve there is a hole, there is an opening, circular opening, and the pipe is joined, pipe is passing through this hole, and the whole opening can be increased or decreased, okay, depending upon the signal which is coming from the controller. So this one is an electrical signal, and depending upon this signal the opening of the control valve will increase or decrease. So if the opening of the control valve is increased, then outlet flow will be increased, and if the opening of the control valve is decreased, then outlet flow will be decreased. Now again there will be a linear relationship between the opening of the control valve and this control action. This one is called the control action or control signal. So if the control action is increased, then opening of the control valve will be increased, and if the control action is decreased, then opening of the control valve is decreased. So let's see what type of valve. This one is one of the valve I am saying, that is if the signal is increased, then opening is increased, and if the signal is decreased, control action is decreased, then the opening is decreased. Okay. There is another type of control valve, just opposite is. That means if the control action is increased, then opening is decreased. If the control action is decreased, then the opening is increased. Just opposite of this. That means one type of valve is this one, If control action is increased, opening increased. If the contraction is decreased, then opening is also decreased. This one is one type of valve. Then another type of valve, if the control action is increased, then opening is decreased. And if the control action is decreased, then opening is increased. This one is another type of valve. Okay. This type of valve is called fail to close. This type of valve is called fail to open. This one is called fail to open, and this type of valve is called fail to close type. That means when control signal is failing or decreasing, then it will be closed. And in this case, when the control action is failing or decreasing, then it will be open. Now, what is the convention in this case, or what is the rule in this case to control this process to our desired height, that is 500 meters? That means if the height is constant or remains fixed at a 500 meter, then at that time we can say the inlet flow rate must be equal to the outlet flow rate. That means when level is 500 meter and it is maintained to that value, it is constant. When it will be constant, when it will be sustained to that particular value, the condition is we have to make the inlet flow rate must be equal to the outlet flow rate. So the condition is inlet flow rate must be equal to the outlet flow rate. So if next one, this one is the one. Next, if inlet flow rate is increased compared to the outlet flow rate, then level will be increased. And if inlet flow rate less than outlet flow rate, then level will be decreased. Okay? That means to maintain the height of this water to a particular value or set point value, we have to make the inlet flow and the outlet flow to be same. And this is done by the changing the opening of the control valve. So the opening of the control valve must be so that then the inlet flow rate should be equal to the outlet flow rate, and that opening again controlled by this control action of the controller. So controller will decide how much voltage or current is to be delivered to the control valve, so that the opening will make the inlet flow rate and outlet flow rate to be same. So we have to make a balance between them, that is inlet flow rate and the outlet flow rate. And this balance is done by the controller, and that decision will be taken by the controller. So there will be always some increase or decrease in the control action if there is some fluctuation of the level. So this is done by this level control loop. Okay. Now let's see if the inlet flow rate is now increased. Suppose suddenly due to some disturbance, the inlet flow rate is now increased. As soon as this inlet flow rate will be increased compared to the outlet flow, then the level of water will start to increase. Okay. And as this one is increased, then the level sensor will give the larger value compared to the previous one, and this value will be compared to the set point value. So obviously this value will be larger. Okay. Then the controller will take the decision. As this one is larger, then we have to now increase the flow rate. Now inlet flow rate is larger than the outlet flow rate. So we have to make the level once again decrease to the previous value 500. Okay. So when it will be done, if the outlet flow rate is made greater than the inlet flow rate, that's why the opening of the control valve at that time must be increased. So if we use the fail to close type valve, then the controller will increase the control action. Okay. As soon as the control action is increased, then the outlet flow rate again will be increased, and it will exceed the inlet flow rate. So as soon as the outlet flow rate is greater than the inlet flow rate, then level will start to be decreased once again. And as soon as this one is reaches to the 500 meter height once again, then the error is again 0. Then controller will make the opening to be constant, and once again the inlet flow rate and outlet flow rate becomes same. So in this way the control action is taken place. This one is a process plant example. Now control valve. Inside this, one thing is important to say in this case. I have forgotten to mention it. That is, this one is a symbol of the control valve. This one is not the actual dimension of the control valve. Okay, this one is not an actual look of the control valve. This one is a symbolical representation of the control valve. Mind it. Okay. Now the control valve, inside the control valve there is a actuator. So which one is the actuator? Now actuator is, you can see this control action will be in the form of voltage or current. So it will be in the form of the electrical form. Now this control action is to be translated into the linear motion of a plug. Actually there is a plug. like this shape. So this plug actually moves up and down through the pipe, through the opening of the control valve. So if the control valve is lifted upwards, then the opening is increased like this. This opening is increased. Suppose this one. This one is completely blocked now. As this one is going upward, then it will be open. The opening is open. And if this one is going downwards, then the opening is decreased. So if this one is the opening, circular type of opening, then suppose this one is the plug, blockage actually. This plug is going up and down, going up and down. This one is the opening. White portion is opening. So there must be a linear motion of this plug. This one is the vertical linear motion of this plug. So this electrical signal should be converted to the linear motion of this plug. So this is done by an electrical motor. So this motor will convert the electrical energy to the mechanical form, and this one is in the form of a linear displacement of the plug. So this electrical motor, which is inbuilt inside the control valve, this acts as an actuator. So this electrical motor acts as an actuator. So now if we change or update our automatic control loop, and one thing is very much important in this case. Okay. What is called disturbance? Okay. What is called disturbance in this case? That means disturbance is that cause for which the controlled variable will deviate from its desired value. So now in this case, which one is the controlled variable? So in this case, controlled variable is level or height. Height of the liquid. Okay. Now tell me which one is the manipulated variable. Okay. Manipulated variable, that means by changing the outlet flow rate, we are controlling the controlled variable. We are controlling the height. How? How is it possible? Which parameter in our hand to control? That means we are controlling basically the outlet flow rate by the opening of the control valve. So that means the outlet flow rate is our manipulated variable. Okay. So manipulated variable is outlet flow rate. When the control valve opening will be the manipulated variable. When we are controlling the flow, when the control variable is now flow, if we are controlling the flow of a process, okay, then at that time we have to control the opening of the control valve. In this case also we are controlling the opening of the control valve, but that opening is directly, this is not directly connected to the process. This is not directly connected to the control variable. control variable is directly depends on the manipulated variable. Which variable directly drive the control variable? Okay, that is the manipulated variable. Okay, opening is controlling the outlet flow rate, and outlet flow rate is controlling the height. Okay, so that's why the outlet flow rate in this case will be the manipulated variable, not the opening of the control valve. When our process is a flow control loop, then opening will directly control the outlet uh, flow rate or a flow through a pipe. In that case, the opening of the control valve will be the manipulated variable. Now, tell me which one is called the disturbance or it is called the load variable. That means disturbance is that cause for which the control variable will deviate or fluctuate from its desired value. So in this case, you can see the inlet flow rate is our load variable or disturbance. Always mind it, load variable or disturbance cannot be controlled. It is not in our hand. We cannot control this type of variables. This inlet flow rate is causing the disturbance to the process. Due to this variable, actually the height of the liquid is going up and down. So that's why the inlet, that is the load variable, or it is called disturbance. In our case, this is inlet flow. Okay, so this load variable is very much important to our process, any process. Okay, if the load variable is not present, it is, if there is no fluctuation in the inlet flow, so there will be no chance of some deviation. Always the height will be constant to the 500. So there will be no fluctuations in the controlled variable. So in that case, we do not need to use a controller. This type of loop is not required at all. So there will be no significance of the control system if the load variable was not present. Okay, so due to this disturbance, always we have to use some control mechanism. So now we have to update our automatic control loop. Just a few. That means the same control loop will be there, only into the process there will be disturbance. We have to add some disturbance. The actuator after the actuator we have the process or system. And into this process we have to indicate our disturbance. This term is actually generating the deviation of the control variable. This one is manipulated variable. Manipulated variable. And after that, yeah, sensor, then transmitter, and the output of the transmitter will be delivered to the one input of the comparator. This value is reference value or set point value. This one is error. And this value is actual value, measured value, measured or actual value. Now we have to see some classification of our system. Before that, I have to mention that this type of block, this block, controller, actuator, process, sensor, transmitter, should be mathematically modeled. Okay. The target of the control system is to represent the entire system, entire closed loop system by a mathematics. This one is called mathematical modeling. Okay, this one is the goal of the control system. If we do not represent a system with our mathematics, then we cannot do anything. Control system is fully dependent of the mathematical modeling of a particular process or the total control loop. So one by one, we have to model the each block. That means we have to represent the each block with some mathematical equation. Okay, this one is the first or primary target of the control system. So before doing that, we have to first focus. The first focus will go to our process, which is to be controlled. This one is the process. So our first target is to model the system or process. For that purpose, we have to move forward step by step. So first step, we have to make some classification of the system or process. So for that purpose, we have to first introduce with the linear system. Linear system. So what is this? So if we have a system, we don't know what is inside the system. This one is a black box. Input is xt and output is yt. This one is a system. Now suppose we are giving the system with two different inputs. One is x1t, and the same system will be given with the another input, that is x2t. Now corresponding to x1t, suppose we have the output, that is y1t, and for x2t we have y2t. Now, first condition, if this one is the case, y1t is the output corresponding to x1t, y2t is the output corresponding to x2t. Then, if we apply the two inputs at a time simultaneously to the same process, then we have this type of output. Now the input is x1t plus x2t. Now the system output, if it is y1t plus y2t, then the first condition of linearity will be satisfied. This one is the first condition of linearity. Okay. Second one is, if the xt input is multiplied with a constant scalar value, some this is c, that is cxt. This type of input is applied to the system, same system. Then, if we get the output is also multiplied with the same scalar value, that is c, yt, then second condition of the linearity will be satisfied. So this first condition is called the additive property, and the second condition is called homogeneity. Homogeneity property. So if these two conditions are satisfied simultaneously, then we can say the system is a linear system. If these two are satisfied, then we can say the system is linear system. Understand? And if we see the first condition, that is the additive property, then we can understand this is the similar to the superposition theorem, right? In case of the superposition theorem, we have to consider the effect of the each input individually. That means this one is the effect. Now, as a whole, the all cause are applied to the system, then the output will be the summation of the each effect. This one is the superposition theorem. Okay, that means we have to consider the effect of each cause, and if we apply all the cause at a time to the system, then we have the effect will be the summation of the each effect, which is happening individually for the each cause. Okay, the same thing is happening in this case. Y1 is the effect of the cause x1 when x1 is applied individually. Y2 is the effect of x2 when x2 is applied individually. Then when x1 and x2 both are applied at a time, then the output will be the summation of the each effect, y1 and y2. This one is the superposition theorem. So we can say a linear system will follow superposition principle. Next, if we combine these two conditions, additive and homogeneity, combined minimally, then we can write A x1t plus B x2t, where A and B both are a scalar constant. This one is a constant. Then, if this type of input is applied, then the output will be A y1t plus B y2t. So this condition is the combination of these two. That means we can say if this condition is satisfied by a system, then we can easily say this system is a linear system. Okay? That means we need not to check these two conditions separately. If we can check this condition only for a system, then we can easily say this system is a linear system. So for any type of problem, we have to follow this condition only. Now we have to solve a problem. First we have to solve our well-known system. That is, when we can say a system is a linear, that means we have very much familiar with the linear characteristic curve. That means if this one is a straight line, it's a contrast point. This one is the output and this one is the input. That means if yt is the output and xt is the input, then this will be the k into xt in this case, for this particular case. We know this system is a linear system. If we have this type of characteristic curve, input-output relationship for a particular system, then we know this system is obviously a linear system. Now we have to prove this one with the help of this one. Now we have a system whose input is xt, example, and the output is yt. Yt is k times of xt. Suppose this system is supplied with an input that is x1t first time, and the corresponding output is y1t. In the same way, if we supply x2t next time, then output, suppose it is y2t. Right? So obviously y1t is k times of x1t, y2t is k times of x2t. Now suppose we have another input which is x3t, and this x3t is this one, that is a x1t plus b x2t. This type of input is now applied to the system, and now the corresponding output, suppose y3t. Now we have to find out the expression of this y3t. So y3t, we can write this one will be k times of x3t. Now put the expression of x3t, this one is this much, that is k into a x1t plus b x2t. Now this one can be written as a k x1t plus b k x2t. Now k x1t is y1t, so we can write a y1t plus this one we can write b y2t. That means we can say now the system is represented in this way. If we provide the input a x1t plus b x2t, then we have output is a y1t plus b y2t. So this will satisfy the composite condition of the linearity. So that's why this system is a linear system. This system is linear. We have proved it. Next one is time invariant. Time invariant. So what is called time invariant system? That means if we have a system, we have supplied an input of xt and corresponding to that xt we have output yt. And if we see this output graphically and xt also graphically, then suppose this one is xt is a step input, suppose this one is step input, and this one is the yt suppose. That means in this case we have applied the input starting from 0, t is equal to 0. And if we have this type of step input which is applied to the system, then we have this type of output. Now suppose this same xt is now applied after t time. Suppose then the input is called x dash t, and now this input is applied after t time. That means this step input will be started from after t time, capital T. This one is the x dash t. Okay. Now, what will be the output? If we have the same output, which is also started from capital T, suppose this output is y dash t. This is the case. If this case is happening, then we can say this system is a time invariant system. So what does it imply? That is, a time invariant system always gives the same input corresponding to the same output irrespective of the sign, irrespective of the time. Any time if we supply the same input, we will get the same output. And this is happening in this case. So now what will be the expression of this x dash t? That means you can see there is a right side shifting by the t parameter. So starting from origin 0, we have a right side shifting of amount t time for this x dash t. If we compare these two signal, if we compare these two signal, then we can say x dash t is a right shifted version of xt, and the amount of shifting is t. So in this case, the expression of x dash t will be x t minus t. This property is called time shifting property. If there is a right shifting, then the t will be prefixed by a minus sign. That is, this will be t minus capital T. And if there is a left shift of the amount t, capital T, then this will be t plus capital T. Okay, this property is called shifting property. Okay, so the expression of x dash t is x of t minus capital T. In the same way, the expression of the y dash t will be how much? That is y of t minus capital T. Y dash t, this one will be y of t minus capital T. So if this property is satisfied, then we can say that is the system is a time invariant system. So let us take an example. Suppose a system whose output is yt and yt is related to the input by this function, that is it is now sine of xt. Sine of xt. This one is a system. Now we have to check either the system is time invariant or not. Let's see. So we have to provide, that means in this case we have to substitute the t by t minus t. We have to substitute the t by t minus t. That means for the time being, suppose we have applied the another input which is x dash t, and x dash t is now suppose it is a time shifted version of xt, that is xt minus capital T. Now corresponding to this x dash t, suppose the output is y dash t. So y dash t is how much? Y dash t will be the sine of x dash t. Done. Now x dash t is this much. So in place of x dash t, we can write x of t minus capital T. Now obviously we can say y dash t is y of t minus capital T, because if we substitute the t by t minus t, we have this much of expression. That means if we substitute, if t is replaced by t minus t, then from this expression we get y t minus t is equal to sine of x t minus t. So that's why we can say x of sine of x t minus t is equal to y of t minus capital T. That's why I am writing in place of sine of x of t minus t is equal to y of t minus t. So that's why the time invariant property is satisfied in this case. That's why this system is a time invariant system. Now, last system is our causal system. Causal system and non-causal system. Causal and non-causal. So what is it? A causal system is the system where the output at any instant of the time depends on the present and past input. That means in case of the causal system, the current or present output depends on the past, past or present input or both. Okay, so it can depend only on the present value of the input, or it can depend only on the past value of the input, or it can depend present and past value, both of them. Okay, so this type of system is called causal system. So what is the non-causal? If the current output or the present output depends on the future input, then this type of system is called the non-causal system. Okay, that means in case of the causal, the current output value depends on the past and present input. In case of the non-causal, current output value depends on the future value of the input. Okay, now how to check it? Let's take an example. Suppose we have a system yt is equal to x of minus t. Now check the system is causal or not. Causal system or non-causal system. Now, how to check? In this case, we have to put some values. Suppose we have to take the time instant, that is when t is equal to t naught. Then we have to find out the expression of yt. What will be? At t is equal to t naught, the yt naught will be is equal to x of minus t naught, as per the equation, this equation. Then now we have to put t is equal to minus t naught. This on first case. Next one, t is equal to minus t naught. Then we have y of minus t naught will be equal to x of t naught. So what does it mean? These two conditions. So if we see the timeline, this one is the t-axis, this one is the origin 0 time. Suppose that t0 is this time. So what will be the minus t naught? T naught will be this time, minus t naught. So if t naught is our present value, so we are now in this position. So t naught is our current or present time. So corresponding to T naught, we have seen the output depends on the input value, which depends on minus T naught. So if we take this time instant in comparison with this time instant is a past value. So in comparison with this one is a past value, past time instant. Okay, so for this past condition, we can say the current or present output depends on the past input. Okay, so for this system condition, past condition, it is depends on the past input. Second one, this one is minus T naught and this one is T naught. So now if minus T naught is our present value, present time instant, then in comparison with this time instant, we can say T naught is our future, because now we are in this time instant. We have to move in this one. So if this one is the 2-second time, then time will be increased. So that's why the T naught time is the future value in comparison with the minus T naught time. So if this one is the present, suppose this one is the present. Sorry, I forget to mention it. So if this one is the present value minus T naught, then with respect to this present value, T naught will be the past. This one is the past. Sorry, this one is the future. So for the second condition, we can say the present output value depends on the future input. So although this system depends on the past, but as it is depends on the future, that's why it is a non-causal system. So the condition of the non-causal system is it must satisfy the future. That means the output value must depend on the future value, although it depends on the past or present, but the output must be dependent on the future value. So that's why it is a non-causal system.